All right. Let's see if you're paying attention. Class.
Yes.
What's up, Danny? I know. I got you there. I got you. All right. So, for everyone following along, paying attention, we're still in calculus class here today. Thank you very much for all the people following along. You like, share, and comment. Just so you know, I'm approaching that point where I might be able to monetize. So I finally reached over 500 subscribers, and now I just got to get everyone to watch the videos, like all the videos, and guess what? Then I will be over the number. Then I'll monetize. Okay, I apologize for people that, yes, you might get a commercial for body groomers or I don't know, what other commercials they have on there?
They have like snackles.
Okay, yeah. So stuff like that. So yeah, so anyway. So apologize if you see weird commercials. Anyway. Continuity. Continuity. So if you're paying attention right now, you would know yesterday when we talked about continuity, it has to do with a roller coaster. Continuity is a roller coaster. A discontinuity means there's a hole in my roller coaster. Do I like holes in the roller coaster? No, I do not. If I'm on a roller coaster, would I want to be on a roller coaster that all of a sudden just falls off?
You die.
Kind of. Depends on where you're at, right? Okay. So if you have like one of those ones with like the little conveyor thing where you just like fall off into the water, yeah, that kind of might be cool. Anyway, but no. Okay, so continuity at a point, times of discontinuity, sums differences, all that other good stuff. Continuity at a point. Any function whose graph can be sketched in one continuous motion without lifting your pencil is an example of continuous function. Or, how about this? A roller coaster with no holes. No jump in the tracks. Okay? Think of it like that, always. Example, continuity at a point. Here it is right here. So I really hate, like this new textbook, their graphs are horrible. Like you could use MS Paint and come up with a better graph than what they are providing here. Anyway, here's what it looks like. And that right there. What does the circle mean at the end of the line?
It's a hole.
It's a hole, right? All right. Is it equal to that point? Say no.
It's a
No.
hole.
For it to be equal at that point, it had to have a...
Limit?
Nope, try again. Closed dot. Thank you. Closed dot. A solid dot. So, point in which that it is continuous, let's see, at 0. So starting at 0, so limit as x approaches 0 from the right-hand side. Okay. As it approaches 0 from the right-hand side. Okay, so what does that mean if it is there? That means that if f of 0 would be equal to 0. So for it to be continuous, it has to be equal to at that point. So from the positive side, so it is approaching from the positive side 0. Okay, let's take a look at another one. 6. Let me see. 1, 2, 3, 4, 5, 6. Here's 6. There you go. Now, at 6, from the left-hand side, that means going this way. From the left-hand side, f of 6 is going to a value, and this value is 1, 2, 3. I think that's a 3, or is that a 4? I can't tell, because their graph sucks. So, my textbook last year actually had better graphs. Anyway, right here. So from here, we have at 0. So between 0 and 6, I have my function. All values of c should be in between there. But not when, from 2, what's going to happen at 2? Right here. It's undefined right there, right?
Okay.
So it's not going to be at 2. And what else is it not at? This point right here. 3. So there is this in between 2 and 3 that does not exist. Do I want that on my roller coaster?
No.
No, because that is, what's the word of the day?
No. Discontinuous.
Discontinuous. Because I want my roller coaster track to be
Continuous.
continuous. Thank you very much. All right. So limit as x approaches c of f of x, we should get some value in between here as it approaches in between those two numbers. So in between here and here, I should have some value c there. In between here and here, I should also have some value of c there. It should be equal to something there because there's not a hole. So if I was on a little bitty roller coaster that only goes from here to here, yay. Okay, another little bit. Okay, like It's a Small World. Okay, only from here to here. There is a value in there. So point at which the f is discontinuous. At 2, it's discontinuous because that thing is an open dot, which is a hole. Yes? Good. That is a hole. So c less than 0. All right, we don't have anything over here less than 0. We don't have anything over here more than 6. That's those things. And right here in between 2 and 3, that's this little piece in between here that is also does not exist. They're outside of my domain. So it's not even on the roller coaster anymore. Okay, that's like the line to the roller coaster where everyone has to sit for like 8 hours. You know, you pay like, I think it's like $200 for Disneyland passes now. And do you know what you really do?
What?
You get 4 rides. In a day, you'll get 4 rides because you're spending about 4 hours, 3 to 4 hours in a line for each one of those places. That's crazy, right?
Yep.
But then all the people buy fast passes, and then there's the extra fast pass. Then there's the frontline pass. But then what if you're one of the plebes that only could just afford to get into the park? They have to wait forever. Okay, not everyone could pay, the $4,200 for Shake It Off tickets. Okay, like other people. Yeah, I see what you did there. Anyway, all the rest of us are low plebeians because we can't afford going to Chipotle every day. Anyway, continuity at a point. Interior. Okay, the function is continuous at interior point C if its domain is in between there. So it must exist the left side and right side. So this is not a one-sided limit. It is a both side. It has to exist for it to be there. Endpoint. A function is continuous, okay, at left endpoint A, or is continuous at endpoint B if its domain, okay, right here. So that means that from the right-hand side, we're going to A, okay, or the left-hand side, we're going to B. Does that make sense or no? All right, let's throw it on the graph instead. So basically, there's A and B. So my graph is going to be continuous. So, according to that thing right there, from the right-hand side, that means the right-hand side is going to this one for A. It's going there from the right-hand side. And for B, it is going to be continuous going B from the left-hand side. Does that make sense?
So like a line.
Yes, it is a line, and it is what?
Continuous.
Continuous. Now, that means that the limit is coming to this point right here. Okay, the limit. So could these ones be open dot or closed dot? Yeah,
Yeah.
it could be open or closed. But for what I'm showing you here, these are open, so it still does exist there, even though it is approaching, but it's not equal to. A function is not continuous at A point C. We say that it is discontinuous at C. C is a point of discontinuity in the whole thing. And C need not be in the domain. So C could also be somewhere over here. So that's outside of my domain. If my line only goes to here, it's like, oh hey, I'm in line for the tilt-a-whirl, and is that part of it? No, I'm not on the tilt-a-whirl. So it's discontinuous for my roller coaster thing. Okay. Now, here are typical types of discontinuity. Removable. We did a removable. Okay. We did a removable yesterday. I believe, what was the problem yesterday? It was like an x plus 3 or something like that.
9x plus 1 over.
It was like this. I think it was like x minus 3 and x plus 2, something like that. I think that's the one from yesterday.
Yeah.
Okay. See this right here? This one, I would have a discontinuity here at x equals what? X cannot equal what number? Y3. What's going to happen at 3? What's 3 minus 3?
3.
It's 0. Can I have 0 here? I can't have it in the bottom, can I? So I cannot have it in the bottom because that is going to be undefined. So therefore, that thing being able to cancel this out is going to be a removable discontinuity there. So this gives me, this is an example of a hole. I removed it, that's still a hole. It's a hole in the trap. Jump. Do you want to be on that roller coaster?
Yep.
Do I want to be on that roller coaster?
No, in reality.
There's the jump. So, all my x values exist, but the continuity is in my y values here because it goes from here up to here. That's a jump. The infinite, what do you think infinite does? Does it go into infinity?
Yeah.
Okay, so is infinity a number?
It's an idea.
It's an idea. So if it's going to infinity, that means it is going to be it's not continuous. There is a type of discontinuity there. The oscillating also was that one where,
Squeeze theorem.
very good, squeeze theorem. Squeeze theorem, where it goes back and forth, up and down, over and over again, where it's actually kind of approaching the number. Okay, there is a discontinuity there because of that. So this is a function. Okay, for A, it's a function. That one works. It is continuous over my whole thing. Bam. This one, I don't know if you can see it. It has a hole right here. This one right here, it has a hole here, but it has a solid die right here. So through my domain, there's all values, but this up here, it's equal to here. So this is a piecewise function. So it's equal to here, but it's not equal to here. There we go. This one. Here's the other example that I'm showing. Solid dot here, open dot here, continuous. Both these going to infinity. Now, this is my oscillating. So if I try to trace this, I'm probably going to end up just like making it like a big, something like that. So discontinuity is there. Because when I get up into here, it's going to keep doing that same thing. So hopefully you guys could actually see this better now because it didn't come out very well on the printing. This one right here, okay, discontinuity of this. This one is important because I could rewrite this like this. Now, what can I not have? I cannot have 1. Why can I not have 1? Because it's going to be 0 in the denominator, right? That would make it undefined. And because of that, I have this, which it goes up like that, and over here it goes up like that. So that means right here, that is called a
Asymptote. Vertical asymptote.
vertical asymptote. Okay, so vertical asymptote. I like to abbreviate because I kind of suck at spelling, so I usually misspell asymptote as like ASSTOTE. Or just an angle side.
Angle side. Limits with 2 items.
So what I did there? Geometry, angle side.
Oh my god, it's been so long.
Angle side. Yeah. Okay. Good. Now, I'm going to stop right here. I'm going to pause for a minute, and I want you guys to go ahead and take a look at some of these questions that we have in the homework. I'm ready.
Okay.
All right, good. So you guys actually had some of this, tried it. Great. Now, there's some things that are actually not in the notes that I want to add to this, which is some of you guys actually got some of these things already. So, Denny, your problem was it INT, right? And I believe it's like limit as x approaches 0 from the right. Was that it? Okay. So, your calculator is super smart. It's a great calculator. It really is. Now, instead of actually going to look through the menu for the integer function, type in int. You can type that in.
Yeah.
int. Okay? So, you don't have to go through looking for it, just type it in. And it does the same thing for a couple other things if you can't find it. So, there's your integer function. And I believe absolute value will also do the same thing. ABS?
Yeah, ABS. Yeah.
ABS will do it? Okay. All right. Continuous function given continuous function because it is continuous at every point in its domain. It does have a point of discontinuity at x equals -2 because it's not defined there. We're looking at this one here. This is going to be my vertical asymptote because I'm going to rewrite this as 2 over x plus 2 times x plus 2, and x cannot equal -2 because that would make it be undefined. And in this case, I cannot remove it. I can't cancel it out like I've done before. X minus 2 is going to be my asymptote here. That's going to be my asymptote. So it is going to be undefined. It is continuous. So my domain of my function has a hole in it. So it can go from there to there, but if I was looking at my domain, we're going to have to start writing it out like this. It goes from negative infinity to negative 2. Now, is it equal to negative 2? Is it equal to negative 2?
No.
No. So how would I close negative 2? How would I close this right here?
Oh, bracket?
Parentheses. The parentheses, bracket is equal to, parentheses is not equal to.
Alright.
Okay? Now, does it pick up again? So if I'm looking at my line, I'm reading my line from left to right. Does it pick up again on the other side?
Yes, it can.
It does. So there is a union where it picks up again. And where does it pick up again?
At -2?
At negative 2. It picks up at negative 2. But what type?
Parentheses.
Parentheses again because it's not equal to, comma, and that goes to
Infinity.
positive infinity. So writing out my domain, I could see what I have here now. So reading this and writing it is super important by knowing and stating what this is. And again, if you notice, I'm not assuming you already know this. That's why I keep going back over things like these, because I already know that there's going to be some holes in your learning that you might not remember it. Okay, you smoked too much crack over summer break and then completely lost all this, right? So these are important. Now we're going to have a couple more. Properties, okay, if the function f and g are continuous at x equals c, then the following combinations are continuous at x equals c. Anything you do with these things, if it's continuous, it's still going to be continuous. You're not going to change it.
Why does sums have a space?
Why does what?
Sums.
I don't know. Yeah, again, I didn't make these notes. This is from the publisher. I like my last year's notes because the graphs are a whole lot better. Anyway, so yes, I'm making fun of this publisher.
Okay.
Okay, good. Anyway, okay, if f is continuous at c and g is continuous at f of c, then composite f of g is also continuous. So, if both are continuous, then when you take a composite, put one inside the other, they're both going to be continuous. Okay, intermediate value theorem. Actually, you know what? I'm going to insert some notes here because there's a couple things that it does not bring up, but I need to bring up because it's not here, and I think you probably already forgot it. Square root. Okay? When I'm talking about anything in a square root, no matter what, anything in a square root, what can I not have inside the square root?
A square?
Nope, try again. Negative. Can't have negative. What happens if I have a negative inside there?
It's an imaginary number.
It's imaginary. I can't do that. So whenever I have that, I know that this has to be greater than or equal to 0. So if I'm plugging in numbers like 6 minus 6 inside the radical, I could have 6 minus 6, right?
Yeah, it equals 0.
0, and square root of 0 is?
0.
Good.
Yeah.
So I know that is going to be a restriction on my domain. That whatever this is, it has to be greater than or equal to 0. So if I'm solving for this, I need to find holes, and this is one way of finding it. What about if I have something like this? Is there a restriction on my domain? Yeah, is there a restriction? Is there something that's going to give me undefined or imaginary?
Negative.
It's not. So for this one, I know it's going to be all real. All real numbers are going to work for that. What about x cubed?
Negative cell.
Yeah. So this one is also all real. What about cube root.
Do that?
Can't have negatives in a square root. Can you have it in a cube root? Yes,
Yeah.
you can.
Okay.
You can, because in a cube root, I could have -2 times -2 times -2, which is a cube root of -8. So that one does work out because there is an odd number. Because you can multiply three negative numbers. You can multiply three negative numbers together, and then because of that, you're going to get another negative. So that one is going to work. So this is also all real.
Wait, so square root, why can't there be a negative square root? Because, which would be 2.
Because this says I need to have two of them, right? Okay, but does that work out if I have... So technically, square root actually has a little 2 here, but it's just... But to get a negative,
One of them has to be positive.
one has to be positive, the other one has to be negative. So for that to work out. So is that 2 of the same number?
No.
No, it's not. And so that's why it does not work out, because you have an imaginary number in a square root. -2 is not the same as +2, is it? They're different places on the number line.
You show me a cube root then?
Okay, so if I have
Wait,
yeah, and so this is going to give me -2 because I have 3 of a kind. That's what cube root is asking for. It's asking for 3 of a kind. Square root is asking for 2 of a kind. Hey, what do you think fourth root's asking for? Of a kind. What about fifth root? 5 of a kind. So if I ask for the fifth root of 32, does that work?
yeah.
You guys don't know your fifth roots right off the top of your head?
It's 2 times 2.
It's just 2,
Yeah.
right? Yeah.
Okay.
Okay, and here, let me erase some of this here.
Just the top.
Actually, okay. So in the other ones, give me that. Let's say that this is going to be 1. Here's the other restriction that we're going to have a lot of. So right here, my denominator what was that? That was weird. And not equal 0. So I could actually have something like this: x plus 3, x minus 2, x plus 1, and the whole thing I cannot have. So I set the denominator equal to 0, and that's going to give me all my places in which that is going to be undefined in my domain. So, does that make sense? Maybe? Kinda? Meow meow? You're like squinting at me. You alright? You're like, give me that dirty look again. Like I just made fun of you for ripping off your buffer again. No? Maybe? Yeah?
Finally.
What hurts? Oh, I'm sorry. Whiplash from that car accident?
Oh my god.
Oh. Are they like standing on your shoulders?
No, I have to launch her quiver and catch her.
Oh, joy.
Launching.
That's always fun.
I got kicked in the neck at the goat yesterday.
Oh. Now, you ready? Meow meow. You're going to tell me right now, x cannot equal what here?
0.
On this one here. What can x not equal in this first binomial? I almost heard what you said. Thank you. -3. What else can it not equal? +2. Anything else? So those are my values of which that it's going to look like. I'm going to have some undefined points, right? Those are where my domain is not continuous. So if I were to draw or write out my domain of this, which is going to be important, is going to start at -infinity. It goes to -3, close union, picks up again at -3, and goes to -1, closed union. -1 goes to 2, closed union, and from 2 to +infinity. Now, again, these are things that I'm having you add to these notes because I'm already expecting you guys probably forgot these. So that's why I wanted to add this to the notes. Ready? Hopefully. All right, let's go. Intermediate value theorem for continuous functions. Okay, a function y equals f of x that is continuous on a closed interval from a to b takes on every value between f of a and f of b. In other words, if f of sub naught is between f of a, f of b, then f of sub naught is somewhere between those two things. If it is continuous, then anything I find in between here for any value between those must also be a value here. Does that make sense or no? Yes? No?
Isn't it the same?
Yes? Maybe? Are you okay with it? If you're not, like, just speak up and say, hey, what the hell are you talking about? You'd be like, what you talking about, Willis? But you don't have to say it like that guy. Okay. So it has to be somewhere in between there. If it is continuous, it is somewhere in between there. Okay? Here it is continuous. That means that if it is closed dot here, for any value that I pick that is in between here, it must be somewhere on my line. It must be somewhere on my line. So if I say a C is somewhere between A and B, and A and B is continuous, it must be somewhere here.
So there's no hole.
There's no holes.
Okay.
Continuous, good roller coaster, right?
Okay.
Yes.
Unless it discontinues.
Not discontinuous. Okay, intermediate value theorem for a continuous function is the reason why the graph function is continuous on all intervals, cannot have any breaks. The graph will be connected a single unbroken curve and will not have jumps or separate branches. Ba-da-ba-ba-ba.
Oh my god.
I'm done. All right, so we're going to use the rest of this time. Please use the time. Don't just sit there and, message everyone you could think of in between now and then. Get some homework done. Okay? When's Tuesday to Friday?
Yeah, it's
Okay.
Friday.
All right, so get to work.